Okay, welcome to the morning session on the final day of ITCS 2020. This session has a theme for about half the papers of sublinear algorithms, and then a variety of topics for the remaining three. The first paper of the session is testing properties of multiple distributions with few samples. And the basic question is pretty much captured in the title, and it's a paper in the field of testing properties of distributions. And rather than just a single distribution, one's given a vector of distributions. You want to know whether they all either satisfy the property or all are far from the property. The next paper is, it's by Mariam Aliakbarpour and Sandeep Silwal. The second paper is Local Access to Huge Random Objects Through Partial Sampling by Amartya Shankar Biswas, Ronit Rubenfeld, and Anak Yodpinyani. And the basic question here is how, intuitive question that this answers, amongst other things, is suppose one has a GNP graph. How do you figure out, get a sampling algorithm that will sample the neighbors of arbitrary vertices, the set of neighbors of arbitrary vertices, even without generating all of the individual probabilities for each of the edges? So if for example, if you're in the GNP model, and P is rather small, you're generating a lot of zeros, a lot of non-neighbors, and you don't want to have to spend a lot of effort to do that. That could be quite expensive. So you want to generate things locally. The third paper is monotone probability distributions over the Boolean cube can be learned with sublinear samples by Ronit Rubenfeld and Arsen Vassilian. And the general question of understanding a distribution on the Boolean n cube, you have 2 to the n points, so there are 2 to the n values, and you want to learn it. That requires learning most of the, about 2 to the n points. But if you know some extra property, in particular, if you know that this distribution is monotone with respect to the cube in the sense of subset containment or bit vector monotonicity, can you actually get a sublinear algorithm in the number of points you need to sample? And in fact, they show that one can get an exponential savings in terms of the in terms of the dimension of the cube. So those three are in the sublinear algorithms area. The third is local to global agreement expansion via the variance method by David Maas and Tali Kaufman. And this considers high-dimensional expanders and the question of propagation of agreement at points of values at high-dimensional expanders on a subset, and how that can be extended to larger sets of the cube, and introduces a method they call the variance method for doing this. There's random sketching, clustering, and short-term memory in spiking neural networks by Yael Hitron, Cameron Musco, Merav Parter, and Nancy Lynch. And so this is in neural net models of the brain, in particular spiking neural nets. And for those of you who were at Stock last year, there was a talk about how fruit fly olfactory areas in the fruit fly have natural analogs in spiking neural nets, and this is in that same general area, and it actually says, how could you actually end up with short-term memory? Gives a model that gives you short-term memory using spiking neural nets. And the final paper of the session is Sample Complexity Bounds for Influence Maximization by Gal Sadeh, Edith Cohen, and Chaim Kaplan. And this is in the problem, considers problems related to influence spreading in graphs and gives methods for analyze general method of sample complexity. If you want to see how influence is spread in a graph under certain models of spreading, you have to run, you can test this via simulations, and how many simulations do you need to run. So, oh, sorry, didn't mean to do that. Well, there we are. So the first talk, testing properties of multiple distributions, will be given by Sandeep Silwal. Thanks.
Hey everyone, this is a joint work with Miriam, who's in the audience also. So I would like to start with some motivation. And I guess our main motivation was that real-world data sets are not identical. And what do I mean by that in particular? So consider Seattle's favorite store, Amazon. And let's say they have a secret database of purchase history of thousands of customers. Now, all these customers are different, right? And we can't just assume that they're all the same person or they all have the same beliefs and wants. And in particular, each customer might shop at the store a number of times. So we have few data points per person. But also, we need these different sources to be similar somehow. Otherwise, there's no hope of gaining any meaningful insights. For example, if we had a data set of health data from patients with very different diseases and conditions, then there's no hope that we can get something meaningful. So the central question that we sort of explored is, how can we model this similarity and all these problems that I outlined, and in the context of distribution testing? So first, I'll tell you all about our method to model the similarity. So we have this structural condition to model the similarity. And in this structural condition, let's say that we have some known distribution Q, which is our hypothesis. And I'll get to that more later on. But let's say that our ith sample comes independently from some distribution Pi. So our structural condition is the following. First, in this example, let's say Q is the uniform distribution that we know. Our structural condition is the following. We partition the domain into two parts, A and B, that we don't know. We just know that these parts exist, such that for all Pi, their probability mass is larger than Q on A and smaller than Q on B. So for example, P1 here would satisfy our structural condition, and so would P2, even though they're different. And in math, this just means that there exist some sets A and B such that what I said is true. So let's see how this structural condition actually falls into the context of distribution testing. Let's say you're a high roller and you go to a casino, and there are various slot machines, and you go to the casino and you play each slot machine once, and you want to distinguish the following two cases. Case one is that the casino is a nice casino, which is rare, which is saying that all these machines are fair, meaning that they assign equal probability to all the prizes. Or you want to test the case that the house or the casino is very unfair, meaning that they assign higher probability to cheap prizes like free drinks and lower probability to cash money. So yeah, does everybody understand everything so far? Please ask questions. Okay, so what are our results? We have some known distribution Q, and we get our ith sample from a possibly new distribution Pi. And we can distinguish the following two cases. Case one is that all the Pis are identical to Q, and the second case is that all of them are far from Q, And by far, we measure in the L1 or total variation distance. And we can do this in sort of the optimal number of samples, where n is the size of the domain. So we're assuming the distributions are discrete. And like I've talked about so far, if I just say that, then that's not going to be true. For example, all the PIs can be very far from uniform, but they can together congregate to look like they're uniform. For example, if all the PIs were just supported on one element, they had all their mass on one element, but the element that had their mass on was different every time, then altogether, once you get these samples, you're getting samples from different elements that look uniform. So we have to assume something about the PIs. And what we assume is that they satisfy the structural condition that I talked about previously. And we have other results in the case that we don't know Q, but we have sample access to Q. And we can also do that optimally, but I won't talk about that. So a very natural question that you might be wondering is our structural condition really necessary? It seems kind of like a very restrictive condition, having this pointwise greater than or equal to, or pointwise less than or equal to. But in our paper, we systematically argue that such a condition, we have to assume such a condition. And I'll give you a brief example of a pretty natural weaker condition that doesn't necessarily work. So let's say that we replace our structural condition with this weaker condition, that here U means the uniform distribution, where if there exists some set A such that all the PIs are far from uniform on that A, and by PI of A, I mean you add up all the probabilities on the set A. So here, this is a weaker condition because I'm not specifying like a pointwise relationship, but sort of like an aggregate relationship. And in this example, I'll show you that you can't do uniformity testing. So the example is the following. P1 will have all its mass on the first element. P2 will have mass 1 over n on the second element, the rest on, 1 over n on the first element, rest on the second element. P3 will have 1 over n on the first two elements and the rest on the third element. And this pattern kind of continues, this wave kind of pattern. And you can check that, so you don't have to do the math. I already did it for you, that this example does satisfy this weaker condition, but also more something that's troublesome is that if we take samples from these distributions, we can compute that the probability that any two samples collide, which means that they're the same, is 1 over n. So why is that a problem? Because that's the same for uniform distribution, right? Probability that any two samples are the same. And in particular for this example, we can also compute that these higher order moments match. And by higher order, I mean probability that like any fixed k number of samples match is exactly the same as you would get in the uniform distribution. So in this case, this weaker condition that doesn't work. And in our paper, we kind of systematically argue about more things. So we sort of have to assume something kind of restrictive like our structural condition. And I forgot to mention, but it's known that if these higher order moments match, then doing any sort of distribution testing is hard, which kind of makes sense because moments somewhat determine the distribution. Not always, but in this case, for this property. So let's go back to our problem. What is our problem? We have these samples coming from PI independently, and we want to distinguish the cases that they're all, let's say, identical to uniform, but you can do any Q, or they're epsilon far from uniform in L1, and assuming PI satisfy the structural condition. So our algorithm is very simple, and it's sort of the same type of algorithms that you'd use in the standard cases where you assume that all these distributions are the same, which is basically you count the number of collisions, which is pairs of samples that match. And the intuition is like sort of the birthday paradox. In the case that these distributions are far from uniform, you expect to see many, many collisions. And more formally, it's just 3 steps. You just take some number of samples, and you reject or accept if you see some threshold number of collisions. The exact number doesn't matter, but it's just a very intuitive idea. So I'll give you a glimpse into the analysis of why it's challenging in our case, and why these tools that already exist for the standard problem don't work in our case. So let's just assume that all the distributions that we're getting samples from is the same distribution, sum p. And you can compute that in this case, the probability that you have a collision, which means you see two samples that are the same, is just the 2 norm of p. And that makes sense if you, well, yeah, it's just some computation. And also, another relatively straightforward computation that you can check later is that if we assume that p is far from uniform, then this actually implies a lower bound on the 2 norm of p via Cauchy-Schwarz. Cauchy-Schwarz. And in this case, what that actually means is that you do get enough collisions to reject in your algorithm. But of course, in our case, all the PIs are different. So this straightforward analysis can work. And in particular, this straightforward idea can also not work. So let's go back to our case where you can have two different distributions, Pi and Pj. And let's compute the probability that samples I and j match, which is just this sum. But in our case, it's possible that each pair, the probability that each pair contributes can sum to 1 over n, which is, again, a problem because that's what you'd get for the uniform case. So I'll give you an example of that. Here, the partition of the domain is A and B. Again, I want to note that we don't necessarily know what the partition is in our algorithm. We don't assume that. But here, let's say the partition is A and B, where it's like the first n over 2 elements and the last n over 2 elements. And P1 has mass 2 over n on the first half of A, 1 over n on the second half of A, 1 over n on the first half of B, and 0 on the second half of B. And P2 is the same as P1, but flipped. And I'm not going to do the computation. Well, it's on the board, but you can also check that in this case, this pair kind of contributes the 1 over n collision. But somehow we argue in our paper that on the aggregate, these collisions add up, and you get the right number of collisions, which is kind of cool. And also in our paper, we have to argue about the concentration of this quantity, which is also challenging, which I won't talk about. So I guess I want to emphasize some concluding remarks, which I think are the highlights of our paper. So we also argue in our paper that modeling a heterogeneous data set is necessary. And if you know anything about this theorem called De Finetti's theorem, I'm not going to explain it here. But we sort of argue that this finite forms of this theorem can't really work, and they have some really bad approximation error. So you kind of have to model distributions that are comprised of many, data sets that are comprised of many distributions. But also on the bright side, it's that maybe our existing algorithms are robust enough to already handle this case. And maybe we don't have to assume all these clean and crisp assumptions of like IID, whatever that we normally do. Because in our paper, we're just taking the standard tools and sort of reanalyzing them with more math. And it turns out it can handle a much harder problem. Yep. And thank you.
Questions for Sandeep? And meanwhile, the next speaker should set up. So I have a question. So you know that some condition is required, a stronger condition. Do you know that the condition you propose in itself is necessary, or would there be alternative? Do you think there are alternative structural conditions which also might apply?
I think there are like some, if you just, I do think there are other conditions, but it would kind of have to be as restrictive as ours. And in the paper, we sort of guide you through that. In the paper, we sort of start with no assumptions and keep adding assumptions until we arrive at our condition. And at each step, we argue that, okay, this is not enough, this is not enough. Oh, wait. Now, okay, we found the sweet spot in some sense.
Did you look at lower bounds by any chance? Like, it looks like square root of n over epsilon squared like might be a natural quantity. So
I didn't mention this, but all these problems that we studied have a natural counterpart where you assume that the distributions are the same. And in those cases, we get that there are no lower bounds, and we match the upper bounds. So we sort of get the lower bounds for free. Thank you.
Okay, let's thank the speaker again. So stand in front of the mic.
I will talk about how to provide local access to huge random objects. This is joint work with Ronit Rubenfeld and Anakio Pignani. So let's consider a huge random object, such as this huge random walk, where it's a one-dimensional walk. You go up and down with probability 1/2 each. And normally you would just generate all of it, generate each step, and then you get the walk. But what if you only care about a few positions? Then it seems inefficient to generate the whole walk, and instead perhaps you would like to provide a query of the form height of t, which returns the height of the walk after t steps. So you give a query, you get some response, and you can have many such queries that appear in arbitrary order. And the only restriction is that all of these responses need to be consistent with some underlying random walk that is drawn from the correct distribution. So if you only care about a few positions, you can sort of skip the pre-processing where you have to generate the whole thing. So formally, we want our queries to be efficient. We want them to take about polylog time, space, and random bits per query. We also require that the responses to each query is consistent, they're all consistent with each other, and with a single valid sample that is drawn from the correct distribution, or at least epsilon close to it. So that's the setup. This is a sort of pictorial representation. Normally you take your generation algorithm normally would take in some parameters and randomness, and it would generate the entire random object, which can then be read by the user to do whatever they wish to do with it. In our paradigm, we sort of query the algorithm directly instead of waiting for it to generate the whole object. So instead of generating the whole object up front, the algorithm only generates the parts that it needs to based on the queries it receives. And eventually, over time, you could provide enough queries that the algorithm ends up generating the whole object and writes it all down into memory. So this is sort of the general model. And right now, I'll talk about some example queries in random graphs, which is going to be the main focus of this talk. So in random graphs, the queries you can ask are, for example, given two vertices, are they connected? Given a single vertex, can you tell me all of its neighbors, or perhaps you just want to know the next neighbor in the adjacency list? Something that we introduce in our paper is something called a random neighbor. Maybe you want to take a random walk on this random graph. So you can ask for a random neighbor of an adjacency of a given vertex. An interesting thing to note is that we can do this even though we don't know how to query for the degree of a vertex yet. Okay, so just briefly, I'll touch on some prior work. This model was introduced by Goldreich, Goldwasser, and Nussbaum in 2003, and they provided some implementations of different kinds of random objects, and as well as some important primitives that we use subsequently. One comment is that many of the results focus on being pseudo-random and computationally indistinguishable from random, and they also allow a limited number of queries. Follow-up work by Nauer and Nussbaum looked at sparse GNP graphs, where the degree is at most polylog. So you can do this all neighbors query, where you report all the neighbors of a vertex, and this is possible because there's only a few neighbors, so you can report all of them efficiently. And this actually gives you all the other queries. So if you know all the neighbors, you can get a random one or the next one or whatever you want. Finally, the most immediate precursor to our work is an implementation of preferential attachment graphs by Evan, Levy, Medina, and Rosen. These graphs have a rooted tree structure, and even though they're sparse, some vertices may have very high degree, which means that this all neighbors query is not good anymore because it would not be efficient. And instead, they introduce this next neighbor query, which is sort of just an adjacency list query. And this model is actually, and this framework, they are actually truly random, and they also allow unlimited queries, and this is also the framework that we will be working under. So now I'm going to start talking about GNP graphs. So just to remind you, this is a graph on n vertices where each edge exists with probability p. So you can think of it as an adjacency matrix filled with Bernoulli random variables, 0, 1 random variables with bias p. The simplest query in this model would be this vertex pair thing, where you're given two vertices, 3 and 5 in this case, Is there an edge between them? Well, you look at the matrix. If you have already revealed that location, you don't care. And if you haven't, then you flip a coin. And whatever you get, the only caveat is you have to copy it across the diagonal, because this is an undirected graph, and therefore you need 5, 3 to be the same entry as 3, 5. So that's very easy. So this is sort of just like a warm-up. Vertex pairs should be very easy in this model, just because everything is independent. More interesting is, I guess, next neighbor and random neighbor, and that is what I'll talk about next. So before that, I'm just going to focus from now on a single row of the adjacency matrix. So given a query vertex, I'll just look at the row of that vertex. So let's talk about next neighbor. Let's consider the case when the graph is dense. P is greater than 1 over polylog. In this case, there's a lot of 1 entries. So it's actually easy to just go through from left to right, flipping coins one by one, until you find the next neighbor. And this takes time 1 over P. Similarly, you can flip coins in random locations until you find a neighbor, and this will give you a random neighbor. So in this regime, it's 1 over P is polylog, so we're good. The other extreme is when your graph is very sparse, and then we can sort of adapt the all neighbors query from the Narrow-Nussbaum paper I mentioned earlier, and then all neighbors will give you all the other queries. So the interesting case really is when P is intermediate, like 1 over square root of n. In this case, you have about square root of n neighbors, and you also have like the gaps between the neighbors is also of size square root of n, the gaps in the row. And this makes it a little more challenging because we want to do little o of 1 over p. Now, so 1 over p is square root of n, but we actually want to do polylog of that. So we sort of want this exponential improvement, and I'll show you briefly how we do it. So let's take this sort of picture we had, and instead of going one by one, what if we could directly jump to the next neighbor? This is not too difficult because the probability of finding k zeros followed by a 1 is just the geometric distribution, which we can sample form efficiently. So we can efficiently find the value k such that this happens because the geometric distribution has a closed form CDF. This is all great. The problem, though, is that this picture is too idealized. Normally, it will not look like this. It will look something more like this, where you have sort of like known entries interspersed amongst unknown entries. Specifically, for example, like this 0 could have been determined by a previous query to the vertex W, and because of undirectedness, it showed up in this row. Similarly, like now if you just go forward and do the skip sampling, you have to figure out how do you resolve the conflicts, because there might be conflicts with the old entries and the new ones. And then what do you do with all these zeros that you're writing down, because the whole point of the skip sampling was to avoid writing down all of these zeros and to skip over them. So I'll talk about how to resolve both of these. Now, given this row, you have sort of like two sort of known entries that might already exist. So there's either 0 entries or 1 entries. And the difference is going to be that the 1 entries, when they're discovered by the other neighbor, they will be reported to you. So when that edge was discovered, it will be reported to the other neighbor. But the 0 entries cannot be reported because there's too many of them. So we will sort of, if we want, we can ask about a certain location and ask whether it's 0 or a question mark, but we don't a priori know all the locations of all the zeros, okay, as the vertex assigned to this row. The first step is to sort of ignore the known entries and just do some straightforward repeated skip sampling until you fill whatever range you're trying to fill. Now that you've done this, you have some conflicts, right? So there are some known entries and some new entries you just created. How do you resolve the conflicts? Well, the immediate thing to do is look at the old red, like the red 1 entries, the ones that were known from before, and those just get immediately replaced. So you know where those are because they were reported to you, and there's a small number of them, so you immediately reinsert them. More interestingly, maybe the red 0 entries are not known to you, but they're only relevant when they conflict with a new 1 entry. So instead, now you loop through the green 1 entries and see if any of them are in conflict with an old 0 entry, and then you replace them. And the intuition is that you're only charging to the number of red 1 entries and the number of red green entries. So your runtime is actually bounded by the number of 1 entries overall. And we'll show later that this is bounded, but in general, like these are the neighbors. So you actually are charging to the neighbors that you are finding and not to the non-neighbors that you're finding. All right. So this basically tells you roughly how to do next neighbor. And I will talk now about how to do the random neighbor query. And this has like one more level of construction where you take the row and you divide each row of the adjacency matrix into buckets such that the expected number of 1, so the expected number of neighbors in a bucket is about O of 1. Chernoff bound tells you that most of the buckets are not empty, and then also that the maximum number of neighbors in a bucket is something like log n. Okay. Why is this useful? Another thing we will always do is whenever we fill entries in a bucket, we will fill the entire bucket instead of trying to do part of it. So how does this help us? The algorithm for random neighbor goes as follows. You pick a random bucket, uniformly at random. You fill it so it might have some known entries, but you fill the rest of the entries. And once you've filled it, you pick a random neighbor. So there's some ones in this bucket, and you pick a random one from amongst them. And you might want to return this immediately, but the problem is all of these buckets are getting the same probability mass, but some of the buckets will just happen to contain more ones than others. So the bucket with more ones is sort of distributing the same probability mass across more neighbors. So this is not uniform anymore. To make it uniform again, we just do some straightforward sort of rejection sampling, where the acceptance probability of this thing is going to be proportional to the number of neighbors in the bucket. And that this gives us the final algorithm for random neighbors. Since you charge the number of ones is bounded above by log n. This is efficient. Some open problems here are doing degree queries, ith neighbor queries, and maybe sampling random subgraphs from within random graphs. I'll briefly touch on some other results. We can extend these GNP results to the stochastic block model and the Kleinberg small world model. And in general, we can do undirected graphs with independent edge probabilities under some mild assumptions. Another set of results we have are focused on random walks and more generally random Catalan objects, which can be seen as, for example, Dyke paths that are just constrained 1D random walks. The nice thing about these is they have bijections to other objects like bracketed expressions. So well-bracketed expressions have bijections to Dyke paths by replacing upsteps by open brackets and vice versa. They also have bijections to rooted trees. You can see the path as being a DFS traversal of the tree on the right. Because of these, we can sort of take queries in Dyke paths, like height queries, correspond to a nesting depth query in the brackets and a distance to root query in trees. We also have something called first return queries, which are more complicated, but that basically tells you when the walk returns to a specified height. And this is actually equivalent to matching brackets in bracket expressions and next child in trees. And one final result that we have is on random colorings of huge graphs. And in this setting, you actually have an input graph G that is huge, and you want to output an uniformly valid coloring of it with Q colors. Now, the query we will support here is given a vertex, return the color, and this query should, on multiple vertices, should all agree with each other, result in a valid coloring that is also random. The interesting thing, though, is that the underlying graph G is too large to actually be read by the algorithm, and instead, it can only be accessed using local probes. So you can't actually read the whole input, so the model parameters are too large, but instead you can do sublinear probes to the input. And in this setting, we actually do get a sublinear runtime when Q is like omega of delta. And then, so just to see what this bound is like, so problem is impossible when Q is less than delta, where delta is the max degree, so you need at least delta colors. And the sequential algorithm works for something like Q greater than 2 delta, whereas our sort of this local access algorithm works for Q greater than something like 12 delta. So there's a gap, but it's not an asymptotic gap. Another feature is that this algorithm is memoryless, so you can actually have multiple independent instances that all agree with each other, but do not have to communicate. So there's an open problem here, is like, can you reduce this dependence on Q? And finally, I'll just leave this list of open problems up. Thank you.
Thank you. Questions for Amartya? And meanwhile, could Arsen please set up?
Just have a very naive question. So you get this output. What information do you have? Do you have the random coloring, or you have a certification that there is some random coloring with these vertices, and similarly for the earlier problems?
So you just each query will each query is for a specific vertex, so you will get the color of that vertex. And if you do n queries for each of the vertices, then you'll actually reveal the colors of every single vertex. And the guarantee is that that coloring will be a valid coloring, and it'll have come from the uniform distribution over all valid colorings. Does that make sense? Or was it?
But you're not going to do n queries, right?
Potentially not. But whatever number of queries you do, like it's as if like the actual coloring exists and you're sort of like accessing it.
I see. So you have a certification that there exists a random coloring that has this information.
And that's a function of the random bits the algorithm uses.
Let's thank Amartya again.
Yeah, thank you very much. So this is work together with Ronit Rubinfeld. And recall the classic problem of learning a probability distribution. So there is some unknown probability distribution rho, and your algorithm is receiving samples from it, and it wants to output an estimate, rho hat. And the guarantee we want is that the variation distance between the estimate and the actual distribution is at most epsilon for some small constant epsilon. So in this setting, it's known that if you don't assume anything about your unknown distribution rho, you need at least omega n samples when n is the size of the domain. So this motivates assuming that rho belongs to some special class and seeing if one can do something there. And to define the class we are working with, recall some standard definitions about the Boolean cube. So for example, here, this is the three-dimensional Boolean cube. It's the set of all strings of 3 bits. And we also, for this talk, we break it into what we call levels, which have the same sets of the same Hamming weight elements of the Boolean cube. And there's the standard partial order among these elements of the Boolean cube. So x dominates y whenever xi is at least yi for every I. And we also call the things that are dominating x the successors of x, and the things that are dominated by x the predecessors of x. And for example, here in this three-dimensional Boolean cube, you can see that 0, 1, 1 dominates 0, 1, 0. And also we use the standard diagram for the n-dimensional Boolean cube. And so the rho is monotone over the Boolean cube if whenever x dominates y, rho of x is at least rho of y. So with this definition at hand, here's our main result. So if rho is a monotone distribution over the Boolean cube, it can be learned with this many samples, 2 to the n divided by 2 to the theta n to the 1/5. And note that this is sublinear in the size of the domain, which is 2 to the n, and we don't know, to our knowledge, there is no pre-existing algorithm prior to our work that accomplishes such a sublinear sample complexity. So here's the outline for the rest of the talk. I will present our main technical lemma, and then I'll talk about how this lemma leads to our algorithm. And finally, I'll present some interesting open problems that our work leaves. So to define our main lemma, we introduce the following concepts of tight and slacky elements of the Boolean cube. Suppose you have some monotone function f over the Boolean cube, then the value of f at x is at least the largest value among all the predecessors of x, right? And now we say x is f tight if this inequality is tight. Otherwise, we say x is f slacky. Now, let me give you a couple examples. Suppose rho is a probability distribution that's uniform on the upper half of the Boolean cube. So if you zoom into this area, right in the boundary of the two halves, then you're going to have an element that has some positive probability, and all the predecessors of this element have probability 0. And therefore, this inequality is not tight, so this element is rho slacky. Analogously, if we zoom into this area that's below, that's somewhere in the bottom part of the Boolean cube, then we have an element that has probability 0, and all the predecessors also have probability 0. So this element is rho tight. And also, if you know about DNFs, then the DNF mean terms of a monotone Boolean function, a function that outputs always 0 or 1, if you think about it, those are the same as the f-slacky elements for this function. So our main lemma builds on the results from this paper by Blai, Hastad, Servezio, and Tan from 2014. So they were studying how monotone Boolean functions can be approximated by monotone DNFs. And it can be stated this way. So suppose f is a monotone Boolean function. Output is always 0 or 1, and it's monotone. So it can be broken into the following two parts: the structured part and the noise part. And the conditions on these two parts are as follows. So noise is positive and also small in this L1 sense. And the structured part is structured in the following way. So every element of the Boolean cube, if it's G-Slacky, then it belongs to only a small number of special levels of the Boolean cube. So only a constant as opposed to n levels that are out there. So our idea is to take this lemma and try to prove something similar for the monotone probability distributions.
What does it mean that its noise is non-negative?
It's just as a function. So it's sum of two functions. Sorry?
So G is not necessarily non-negative, or?
G is also positive. So it's a one-sided noise.
Okay.
One other way to put it. Okay. So the first attempt to try to extend this to monotone probability distribution is to just copy everything and change the scaling to make sense for monotone probability distributions. So that would be that every monotone probability distribution row can be broken into a structured part and a noisy part. So noise is positive and small. And if the structured part, if x is G-Slacky, then it's in one of the only constantly many special levels. Then unfortunately, this is wrong. This is actually not true. And we have to fix that by introducing weights. So we introduce a weight to each of the level, assign a weight to each of the levels of the Boolean cube. And instead of bounding the number of these special levels, we bound their total weight. And then a similar, with appropriate choice of the weights, the similar lemma turns out to be true. So now let me sketch how this lemma roughly leads to an algorithm. So let's zoom into this segment of the Boolean cube in between of two such special levels. So then also assume there is no noise. The noise happened to be 0 for simplicity. So then you have that this level in the top of the segment has row-Slacky elements, and this level below on the bottom of the segment also might have row-Slacky elements, but all the elements in between of these two levels are row-tight. So if you pick some x in this segment, then if you you pick y, so that y is a predecessor of x, and y belongs to this lower level of the segment, and also the value of rho is the largest among all such y's. So to maximize rho of y subject to these two constraints I just mentioned. So if you think about it, the fact that all these elements in between are row-tight will imply that rho of x equals rho of y. And also by monotonicity, the value of rho in between x and y is sandwiched between rho of x and rho of y, and since those things are equal, then it has to be the same. It has to not change in this area. And so if we color it in green, we can say that rho of x equals to the average of value of rho in this green area. And note that this really uses the fact that y was chosen subject to those two constraints to have the largest rho of y. If it wasn't the case, then we would only have an inequality. So this average would be a lower bound on rho of x. So with this, so now our idea is to estimate rho of x by estimating this average value of rho between x and y. And so there are like many questions here. Like we don't know where the special levels are, and we don't know where y is. And the question of how we find this y is we essentially try all of them. And since each of them provides a lower bound for the rho of x, we go for the best lower bound. And all the other problems are handled in the analysis of the algorithm. So let me summarize the algorithm that we have. So recall this was the number of samples, and define eta xy as the average value of rho in this region between x and y. And at the head xy is this empirical approximation for it. Okay. And so this is our algorithm. So rho hat x is this maximum of eta hat xy subject to y is the predecessor of x, and the Hamming weight of y is Hamming weight of x minus some parameter L of x. And this parameter L of x is dictated by these weights we have in our main lemma. And L of x only depends on the Hamming weight of x. So now some open problems. So first obvious question is, what's the tight bound? To our knowledge, the only lower bound known on sample complexity is to the point 15n. And what about computational runtime? How much can you achieve there? And what about other problem set? There's some existing work on the total order and low dimensional hypergrids. So what about, for example, 0, 1, 2 to the n? What can you do? What can you say about this partially ordered set? And finally, there are these couple problems, estimating support size and estimating distance to uniformity, that are easier than learning, because if you have a learning algorithm, you get an algorithm for these problems for free. And the question is, can you bypass learning and can you achieve better sample complexity? And we do achieve sample complexity that's better than our learning algorithm. So what's the best that can be achieved for these problems? Thank you very much.
We have time for a few questions.
Yeah.
So do you have any intuition or like short explanation of what the right weights are to choose when you're like, taking this decomposition into noise and structured parts?
Yeah, I feel so it ends up being dictated by this internal logic of how this structural lemma is proved,
Okay.
on one hand, and on the other hand, by the weights you need to make the algorithm work. So they end up being quite non-trivial because they have to achieve both of those things. And I'll be happy to talk about it later. If someone wants more details.
Other questions? Meanwhile, David, could you please set up? Other questions? So I have a question. How do you find the levels at which to search for the y?
Yeah. So. Sorry. So. Our algorithm ends up being oblivious to that. So we choose this parameters L of x. So the actual analysis ends up being if you got lucky, and there's none of these lucky levels high enough, then it works. And if you don't get lucky, we argue that the estimate is not terrible. And as long as it's not terrible, the lemma guarantees that the systematic error introduced will not be too bad because there cannot be too much weight of the probability distribution of those things.
Okay. Well, thanks very much. Thanks again.
So I'll talk about agreement expansion. Okay. It's a joint work with my PhD advisor, Ali Kaufman. All right, so I start with explaining what agreement expansion is. We have a ground set of vertices and some collection of sets of size D. And we are given some, for each such set, we have a local function. So for each set S, we have a local function f of S, which specifies a 0 or 1 value to each vertex in this set. And the notion of agreement expansion tells us basically that if most pairs agree with each other, so all but epsilon pairs agree on the intersections, then it means that there is some global function on the entire universe, which explains most of the local functions. So in this case, we can have some global function which agrees with almost all of the local functions. So that's an agreement. That means that this set system is an agreement expander, and it was an important question to find such set systems which are sparse and they are agreement expanders. And by sparse, I mean that it has a linear number of sets. So we can think of it as every vertex is participating in a constant number of sets. So that was the question, to find such set systems, and in order to answer which set systems have this property, I need to present simplicial complexes. That's the object we study. So what's a simplicial complex? We have a set of vertices, we have sets of size D, and it also has the property that it's closed under containment, meaning that we have also all the subsets in this complex, and we connect them by containment. So that's a simplicial complex, and an important ingredient in simplicial complexes, which allows us to argue about properties of these complexes, is a link of each. So each such face, each such subset is called a face of the complex, and I need to present the link of a face, which basically means it's local view. So for instance, we look at vertex 6. What's its link? What's the local view of 6? So we mark all the faces that contain this vertex, remove all the rest, and then remove the vertex itself. So we get another simplicial complex, which is a subcomplex of our original complex. It's of one dimension less in this case, and it corresponds to the local view of this vertex of the complex. So that's the link. And when talking about high-dimensional expansion, so when do we say that such a complex is a high-dimensional expander, there are some different notions. I want to focus on one notion, which is called local spectral expander. I'm not going much into the details, but basically we say that such a complex is a high-dimensional expander if all its links, we look at the graphs induced in these links, and if they are expanders, we say that this complex is a high-dimensional expander. And the first work that related these two notions of high-dimensional expansion and agreement expansion is the work of Dinur and Kaufman. And roughly speaking, I'm not getting into the details, roughly speaking, they show that if we have some very strong expansion properties in the links of a complex, it implies that the complex is an agreement expander.
I missed something in the definition of agreement expander. Is this against like the most malicious F or the average case F?
So it's for every F.
So someone who doesn't like you picks an F and tries to sabotage.
Right. So I wanted to hold. I didn't. It has to hold. The set system has to have this property for every F. Right. So it's the worst case F. Okay. So they showed a relation between high-dimensional expansion and agreement expansion, and the very recent work weakened these expansion properties. So they already showed that some weak expansion properties in the links, I don't get into the details which properties exactly, but some weak expansion properties in the links, they also imply agreement expansion. But then our motivation is the following. Such sparse set systems, which are high-dimensional expanders, are very rare. And we know that the main and strongest example of high-dimensional expanders are what's called Ramanujan complexes. They actually don't meet the expansion properties required by previous works. So even though we have works that show that high-dimensional expansion imply agreement expansion, it doesn't hold for the known and maybe most studied example of high-dimensional expander. So what we ask is the natural question, are Ramanujan complexes, which are the main example, are they agreement expanders? And we answer yes. Our main result, we do it by a local to global theorem. We basically show that if all the links of a high-dimensional expander are agreement expanders, then we can deduce that the whole complex is an agreement expander. And specifically, this does hold for Ramanujan complexes because their links are agreement expanders. So, and the proof goes by some tool that we developed, which is called the variance method. So I'll spend the rest of the talk to, I'll show what is the variance method and how we use, basically how we use it to show this theorem. So what's the variance method? It's I think it's a very nice and clean idea. So basically what it says that if we have some function on like we have a high dimensional expander, and we have a function on its top faces, on the D sets, then what we have that the variance of this function when looked from the point of view of the vertices shrinks by a factor of D. Meaning if we define maybe a new function, G on the vertices, such that for every vertex we basically take the average on the faces that contain it, then we have that the variance of G is sort of the variance of F divided by D. Okay, so how do we use, I'll show how we use this method to prove this local to global agreement expansion. So the idea is like that. We are given some collection of functions f of s for each such set S. And what we want to show that there is some global function that agrees with most of the sets. So which function do we take? Natural function is to take the global majority function. So for each vertex, we look what the majority of the faces, what value they give it, and we use this as the global function, global value for this vertex. And we know by the local agreement that every vertex U has some opinion on every vertex in its link, which by the local agreement condition, we know that it agrees with most sets that contain this vertex U. So for every vertex U, it has opinion locally on all the vertices in its link, which agrees with the faces that contain it. And essentially what we need to show that there is that these local functions on the vertices U agree with the global majority function. So if we take randomly a vertex U, most likely it agrees with the majority, the global majority function. And by simple union bound, it reduces to show that if we take two vertices, U and V, so the probability that the opinion of U on V will differ from the global majority on V is at most supposed to be bounded by epsilon over D, and then we get what we want. So I show how the variance method helps with that, with that picture. So we pick a vertex V, and we look at its link. So we have in the link, we have vertices, and we have these top faces of size D. And we look at the majority function. So some sets of size D agree with the majority function. Some sets disagree with the majority function. Most of them should agree with the majority function. That's the definition of majority. And the function we look at is the indicator function on these sets. So if a set agrees, we give it a value 1. If not, value 0. And now, by the local agreement expansion, we know that basically we have only two cases when we look on the vertices. Each vertex, if you recall, has a local agreement function that agrees with most faces that contain it. So it can be either two cases, or that it sees many green, good sets, or that it sees many red sets. It can't be somewhere in the middle, because then its local function won't agree with most sets that contain it. So it has to be one of these cases. And then by the variance method, we know that the bad event, that it sees many red faces, happen with probability at most epsilon over d, because that the variance of this indicator function on these sets shrinks by a factor of d when looked on the vertices. So that gives us basically our result, that what we needed, that this probability is bounded by some epsilon over d. So just to summarize, we were very interested in the question which sparse set systems are agreement expanders. We noted that the known constructions of high-dimensional expanders do not meet the required properties of previous works. And so we proposed a local-to-global theorem, which we showed that if the links are agreement expanders, it implies that the whole complex is an agreement expander. This specifically applies to Ramanujan complexes, and we've done that by the variance method, which we introduced, and as a future work, this method is very nice. I think it should. We hope that it would have more applications for other problems. All right. Thank you for your attention.
Okay, time for a quick question while the last speaker sets up.
Is it possible to look at this question as some sort of concentration bound? Because to me, it seemed like this local agreement condition was kind of like a bounded difference property, and kind of what you're proving was some concentration bound. I don't know if that's a useful viewpoint.
Well, the variance method is sort of a concentration bound.
Right, okay, so I was wondering if there are more connections or... Okay, thank you.
Any other questions? Okay, let's thank David again. And we'll hear about random sketching from Yale. Thank you.
So today I want to talk about compression and clustering in the model of spiking neural networks. And this is a joint work with Nancy Lynch, Cameron Moscow, and Merav Parter. Okay, so neural networks has been studied in different academic communities from different perspectives. For example, studying the structure of neural networks, mathematical modeling, artificial neural networks. And in this work, we considered the algorithmic aspects of biological neural networks. So we follow the line of work which study biological neural networks, but from a distributed algorithmic perspective, where we do so in the simple yet biological plausible model of spiking neural networks that was first introduced by Mas. And specifically in this project, we considered the tasks of compression, clustering, and input memorization, which are considered fundamental problems in computational neuroscience. And in order to get a better theoretical understanding of these problems, we demonstrated a network construction that solves these tasks. Okay, so I'll start with defining the model. A spiking neural network can be thought as a directed weighted graph, where the nodes are the neurons, the edges are the synapses, and the edge weights indicate the synaptic strengths, where in addition we have a biological constraint that each neuron is either excitatory, meaning all outgoing edges have positive weight, or inhibitory, where all edges have negative weight. And the traditional way to think of a neuron is a probabilistic threshold gate, where each neuron has a bias value, and this will be the threshold. And we define the neuron's potential or membrane potential to be the difference between the incoming weighted sum of its neighbors that fired and the neuron's bias. Then each neuron fires with a sigmoidal probability that depends on the neuron's potential. Okay. And regarding the network dynamics, at the beginning of the simulation, we are giving the initial firing state of all the neurons. And this can be thought as a binary vector indicating which neurons fire at the beginning. And then the network evolves in discrete synchronous rounds, just like a Markov chain, where in each round, each neuron computes the incoming weighted sum of its neighbors that fired and fires accordingly. Okay. When we talk about computational problems in this model, usually we are giving a set of special neurons X, a special set of output neurons Y, and the goal is to construct a network that solves some target function between the input neurons and the output neurons, where the complexity measures that we look at are the size of the network, meaning the number of additional neurons, of auxiliary neurons that we use, and the time, meaning the number of rounds it takes the network to converge into the solution. Within this framework, we considered the neural clustering problem, where we have a set of n input neurons, X, and we think about them as representing binary patterns. We have a set of k output neurons, Q, and we think of k as much smaller than n. And our goal is, first of all, to map each input pattern into unique output neuron, where we want to map similar inputs to the same output and different inputs to different outputs, where when I say similar or different, I'm referring to the relative Hamming distance between them. Okay. For simplicity in today's talk, I'm only going to consider a simplification of this problem, where we assume we have only k different input patterns with relative distance, at least delta, and delta is going to be a parameter of our network. So the key challenge here is going to be to map a pattern that is reintroduced to the same output neuron while mapping different patterns to different output neurons. The neural clustering problem is also motivated by novelty detection, where we want to detect a situation where our input is very different from all the inputs that we're seeing so far. And this was recently studied in the fruit flight olfactory system, which is the sensoring system for smelling. I like to note that this problem can be solved using a neural clustering network, where we map similar inputs to the same output. It has been conjectured that in the fly system, this is done using random projections and a winner-takes-all approach for spacification. And our construction is very similar to this high-level idea, at least the first part of our construction. Okay, so what did we show? We showed that there exists a network solving this problem with probability y minus epsilon, using approximately 1 over delta to the 1.5 additional neurons, and approximately 1 over delta time, where when I say time, I mean the number of rounds it takes the network to converge for each input. So this is the number of rounds I need an input to be presented before I move to the next one. And I would like to note that all our complexity measures does not depend on the input size. They depend only on the Hamming distance, the number of output neurons, and the probability. So for very large inputs, that can be done in a sublinear time and space. Okay. So in the high level, our network consists of 3 steps. In the first step, we take the input of size n, and we convert it to a smaller set of to a smaller set of neurons y, and we do so using a random projection. Then we take this set of intermediate neurons y, and we map them into a sparse vector z with the same size. And we do this using a spacification step. Finally, in our third step, we take this set of intermediate sparse vectors z, and we map each pattern into a unique representative. And we do so in a sequential manner, meaning the first input is going to be mapped to the first output, the second input we see is going to be mapped to the second one, etc. So we also needed to implement a memory mechanism in order to remember the association between inputs and outputs. Okay, so in the remaining time, I would like to give a little bit details of each one of the steps. So in the first step, we have the input of size n. We introduce a set of intermediate neurons y of size approximately 1 over square root of delta, and we connect x and y using a complete bipartite graph, where the weights are drawn from the chi-square distribution with 1 degree of freedom. And the reason that we use chi-square distribution instead of, for example, the normal distribution is because we have the biological constraint that the weights has to be either all positive or all negative. So we simply just use a non-negative distribution. Okay, now this set of neurons Y with good probability have a nice property that the neuron that is going to have the maximum potential value is going to be different from different input patterns. And remember that in this case, the potential is simply the incoming weighted sum of the neighbors that has firing neurons in the input. And because the neuron that has the maximum potential is going to different, with good probability, also the neuron with the maximum firing rate is going to be different for different inputs. Okay, so now in the second step, we take the set of intermediate neurons Y, and we like to convert them into a vector Z of the same size, where the only neuron firing in Z is going to correspond to the neuron in Y that has the maximum firing rate, meaning that it fires in the biggest frequency. In order to do so, we connect each neuron Yi into a history chain Hi of size t, where the number of neurons that fire in the history chain is going to encode the number of times Yi fired within a span of t rounds. Then we're going to select the winner, meaning the neuron with the maximum firing neurons in his history chain, using simple pairwise comparison. So now we have a vector Z that is a unit vector, and with good probability, we have the guarantee that for different inputs, this vector is going to be different. And our goal is to map this set of neurons Z into the output neurons Q1 to Qk, where the goal is to map a pattern that is reintroduced to the same output, while mapping different patterns to different outputs. In the high level, we connect the input Z and the output Q using an association layer, where for each pair Zi and Qj, we introduce an association neuron Aij, and the output is going to fire if at least one of its associated neurons fired. And now, in order to remember the association, we also added a memory mechanism that remembers which pattern was mapped to which output. And in order to prevent other patterns to be mapped to the same output, this memory mechanism also inhibits, meaning it has negative weight to all other association neurons that are associated with the same output, in order to prevent them from firing in the future. And in order for the mapping to be consistent and also sequential, we connect the output neuron with negative weights, so each output is going to have a negative edge to the consecutive output neuron, and this is also called lateral inhibition, and it is well used in neuroscience. Okay, so this is a high level. I will only want to mention that this network can be modified in order to map similar inputs to the same output, solving the neural clustering problem. Also, our memory mechanism has a nice property that patterns that are not seen for a fixed long duration are just forgotten, and then we can use this output neuron in order to map other patterns that we see in the future. So we also implemented some sort of short-term memory mechanism. This network can also be modified in order to implement a biological Bloom filter, and this problem was also considered in the fruit flight olfactory system, and so this gives us another connection between the biological assumptions and how we can implement them. Okay, so in summary, we had 3 steps: a random projection step, a specification using winner-takes-all, and a sequential mapping step where we also implemented a memory mechanism. Thank you.
Thank you. Questions for Yael?
So in your random projection step, you generated weights from the chi-squared distribution, would
Yeah.
it also make sense to like generate the same distribution, but then multiply like all the weights from an outgoing edge by like a random sign?
What? Sorry, I didn't.
Oh, okay, yeah, for the weights, like
Yeah, for the
outgoing
weights.
from a node.
Mhm.
In order to get all their signs to be consistent, would it make sense to multiply by like a random sign?
So I'm not sure. I guess so, but the thing is that we just needed to be consistent with the signs. So if I multiply it with random signs, maybe I'll not get the guarantee that everything will be positive, if I understood. But this can be done in many ways. Maybe we can do it in different ways. The reason also that we use the keystword is because it will be close to uniform, and we also needed another nice property that I didn't mention, that we need a gap between the largest potential and the second largest potential for the sparsification step. So we needed a distribution that has also this nice property.
Okay, let's thank you all again.
So good morning. My name is Gal, and I'm going to be talking about sample complexity bounds for influence maximization, joint work with Idit Cohen and Chaim Kaplan. Oh, yeah, sorry. Can you hear me? Great. So let's start with an intuition. Assume I have a really big social network such as Facebook, and I'm a user and I post something, so my friends read it, and some of them like it and share it, and then their friends read it and share it, and so on. That's way my post is spread through the network, and we can measure the impact I have on the network by the number of people who eventually read my post. So the influence maximization problem is basically finding a group of people who together have the maximal impact or influence on the network. Usually when we talk about this problem, we have to specify how the data is spread through the network, and there are a lot of models to do that. And in this short talk, I'm going to talk about a few of them. In this figure, don't be afraid of this slide, by the way. Every circle represents a diffusion model that has some properties that's nice properties of diffusion, and our results are relevant to some of the circles here. So let's start with the very basic one, called independent cascade or IC model. So IC model is a social network or a graph with nodes and edges where every edge has its own probability, and from this model we generate samples. And the samples are generated by taking live edges according to the probabilities the edges have independently. So you should think about the model as distribution over graphs, where the samples or the graphs don't have probabilities. Let's see an example. If I have this IC model, I can generate 3 samples, and notice that edges with high probability are going to be taken for most or all of the samples. For example, if I have an edge with probability 1, I'm going to take it for all of the samples. And if I have edges with really small probability, they are not likely to appear in my samples. So now let's see a generalization of this to B-dependence models. In B-dependence models, I have sets of edges where each set is at size of maximum small b. And now I take either all the edges in a set or none of them when I draw a sample. Let's see an example. So you can see that in my samples, I either have all the edges from the same color or none of them. This is the generalizations of the IC model, because if b equals to 1, it's exactly the IC model. So now that we know what models are and what samples are, we can start talking about a diffusion itself. So the first thing we should do is choose a seed set, which is usually a set of nodes. In this simple example, I choose just one node, U, and the first thing I do is activate the node, and in the next step, I activate all its neighbors, and so on. And in the second step, I activate their neighbors, and so on. And usually we will look about models that stop after a certain amount of steps, and we measure the reachability or the influence as we denote by R tau of the seed set, the number of nodes we reached in a sample after tau steps. So let's do it more formally. We denote by reach tau in sample G of the seed set as the nodes we reached from the seed set in the sample after tau steps. The reachability value will be the number of nodes we reached. You should think about the reachability as a random variable that depends on the sample. And the influence is going to be the expectation of the reachability values of the samples drawn from the model. Nice. So let's generalize it even more. The most general model is called stochastic diffusion models, or shortly SDMs. In those models, we have distribution over activation functions, where activation function is a binary set function that's specified whenever we should activate a node or not, depend on the other node. In the example I have there, we activate the red node if both edges are activated, unlike the previous models. By the way, the edges here just help us to describe the activation functions more nicely. They're not really necessary in this model. And another generalization is that the influence and the reachability is not the number of nodes we reached, is a utility function applied to them. So the reachability is defined as follows, and the influence is defined correspondingly. Great, so the last model I'm going to talk about called independent strongly submodular SDMs. So basically those are SDMs with three properties. First, the activation functions for each node are drawn independently. Second, the generalization influence function is monotone and submodular. And third, when we activate some nodes, we can create another model, which we'll call reduced models. The reduced model is not a sample, it's a model. And in the new model, the influence function is also monotone and submodular. So if I have those three properties, we call it independent strongly submodular SDM. So now we can talk about the problem formally after we're done talking about the models. So the influence maximization problem is finding a set of size S in a certain model that has small relative error epsilon to the optimal influence with a confidence at least delta. And we're interested in finding algorithms that take as input samples and solve the influence maximization problem. And the sample complexity is the number of samples we need to solve it. So our main results show that the sample complexity for independent strongly submodular SDMs is S, the size of the seed set, multiplied by tau, number of steps, epsilon to the -2, multiplied by ln of n, number of nodes, over delta. Where previous results show that they're basically the same bound, but instead of number of steps, the number of nodes. And this is kind of a novel improvement because number of steps is usually really, really small. Think about the Facebook example. If I post something, it won't be taking more than 50 hops until the diffusion process stops. So tau, in this case, will be equal 50 and not the number of nodes, which it can be millions. There are some models like the IC models where there are tailored algorithms with better sample complexity, but those algorithms fails when we add small dependencies between the edges, like in the B-dependence model. So actually, we have more results. So the first row in this table I just told you about, it's about the independent strongly submodular models. But in general, for any SDM, that we can bound the variance of the reachability of the form appears up there. The sample complexity is, instead of the tau, that's C. And for example, the B-dependence model, this C equals to TB multiplied by tau. And notice that the B-dependence model is not an independent strongly submodular model because we have small dependencies between the edges. Another example is a mixture of R-independent strongly submodular SDMs, where mixture models is basically having a lot of models and choosing one of them uniformly at random. The best way to think about it is, let's think about the Facebook example. If I post something about sports or about politics, my post is going to diffuse differently in the network. So I have several models that model it, and I choose one of them at uniformly at random. So the last thing I'm going to talk about is the computational efficiency of influence maximization. So till now, we just talked about the sample complexity, but I didn't tell you how we actually solve the influence maximization problem. So this problem is proven to be NP hard to approximate better than 1 minus 1 over E. And greedy algorithms that iteratively selects a node with epsilon approximate maximum marginal influence achieve a close approximation, 1 minus 1 over E minus epsilon approximation in poly time, and not exponential time. And our main contribution is we showed that for greedy algorithms for submodular models with low variance, like independent strongly submodular or general SDM with low variance, the sample complexity is s to the third to 3 multiplied by this constant multiplied by the constant c, which is the one we saw in the previous slide samples, and we have a better algorithm, another algorithm that achieves with better sample complexity that uses a factor of s and not s to the third. That achieves the optimal sample complexity we showed, but it's inefficient. It's run in exponential time, and the main question is, can we implement greedy better, which means with the optimal sample complexity bound. Thank you.
Questions?
So what are some of the common functions that are used in the independent strongly submodular model? Like what are some of the generalized influence functions H?
I'm not sure I understood the question, sorry.
Oh, okay. You had a slide with generalized influence functions H. What are some of the examples of functions that are
you
used?
you can think about that some of the nodes have more weight than the others. So if I reach some nodes, it contributes to the influence more than others. This is one example. Or if I reach 2 nodes, it also contributes more to the influence. That answers your question, or?
More like what are some common examples of H?
That's the example of H. Or we can take it off.
Other questions? Maybe we can take the rest actually over break, and we'll resume at 11.